Histogram.
In statistics, a histogram is a graphical representation of the distribution of data. It is an estimate of the probability distribution of a continuous variable and was first introduced by Karl Pearson. A histogram is a representation of tabulated frequencies, shown as adjacent rectangles, erected over discrete intervals, with an area proportional to the frequency of the observations in the interval. The height of a rectangle is also equal to the frequency density of the interval, that is, the frequency divided by the width of the interval. The total area of the histogram is equal to the number of data. A histogram may also be normalized, displaying relative frequencies. It then shows the proportion of cases that fall into each of several categories, with the total area equaling 1. The categories are usually specified as consecutive, non-overlapping intervals of a variable. The categories must be adjacent, and often are chosen to be of the same size. The rectangles of a histogram are drawn so that they touch each other to indicate that the original variable is continuous. Histograms are used to plot the density of data, and often for density estimation, estimating the probability density function of the underlying variable. The total area of a histogram used for probability density is always normalized to 1. If the length of the intervals on the x-axis are all 1, then a histogram is identical to a relative frequency plot. An alternative to the histogram is kernel density estimation, which uses a kernel to smooth samples. This will construct a smooth probability density function, which will in general more accurately reflect the underlying variable. The histogram is one of the 7 basic tools of quality control.
Etymology.
The etymology of the word histogram is uncertain. Sometimes it is said to be derived from the Greek histos, anything set upright, as the masts of a ship, the bar of a loom, or the vertical bars of a histogram. And gram, drawing, record, writing. It is also said that Karl Pearson, who introduced the term in 1891, derived the name from historical diagram.
Examples.
The U.S. Census Bureau found that there were 124 million people who work outside of their homes. Using their data on the time occupied by travel to work, Table 2 below shows the absolute number of people who responded with travel times at least 30 but less than 35 minutes is higher than the numbers for the categories above and below it. This is likely due to people rounding their reported journey time. The problem of reporting values as somewhat arbitrarily rounded numbers is a common phenomenon when collecting data from people. This histogram shows the number of cases per unit interval as the height of each block, so that the area of each block is equal to the number of people in the survey who fall into its category. The area under the curve represents the total number of cases, 124 million. This type of histogram shows absolute numbers, with Q in thousands. This histogram differs from the first only in the vertical scale. The area of each block is the fraction of the total that each category represents, and the total area of all the bars is equal to 1, the fraction meaning all. The curve displayed is a simple density estimate. This version shows proportions, and is also known as a unit area histogram. In other words, a histogram represents a frequency distribution by means of rectangles whose widths represent class intervals and whose areas are proportional to the corresponding frequencies. The height of each is the average frequency density for the interval. The intervals are placed together in order to show that the data represented by the histogram, while exclusive, is also contiguous. For example, in a histogram it is possible to have 2 connecting intervals of 10.5-20.5 and 20.5-33.5, but not 2 connecting intervals of 10.5-20.5 and 22.5-32.5. Empty intervals are represented as empty and not skipped.
Mathematical definition.
In a more general mathematical sense, a histogram is a function that counts the number of observations that fall into each of the disjoint categories, known as bins, whereas the graph of a histogram is merely one way to represent a histogram. Thus, if we let n be the total number of observations and k be the total number of bins, the histogram meets the following conditions.
Cumulative histogram.
A cumulative histogram is a mapping that counts the cumulative number of observations in all of the bins up to the specified bin. That is, the cumulative histogram μ of a histogram Mj is defined as
Number of bins and width.
there is no best number of bins, and different bin sizes can reveal different features of the data. Grouping data is at least as old as Graun's work in the 17th century, but no systematic guidelines were given until Sturgis's work in 1926. Using wider bins where the density is low reduces noise due to sampling randomness. Using narrower bins where the density is high, so the signal drowns the noise, gives greater precision to the density estimation. Thus varying the bin width within a histogram can be beneficial. Nonetheless, equal width bins are widely used. Some theoreticians have attempted to determine an optimal number of bins, but these methods generally make strong assumptions about the shape of the distribution. Depending on the actual data distribution and the goals of the analysis, different bin widths may be appropriate, so experimentation is usually needed to determine an appropriate width. There are, however, various useful guidelines and rules of thumb. The number of bins k can be assigned directly or can be calculated from a suggested bin width h as. The braces indicate the ceiling function, which takes the square root of the number of data points in the sample, used by Excel histograms and many others. Sturgis' formula is derived from a binomial distribution and implicitly assumes an approximately normal distribution. It implicitly bases the bin sizes on the range of the data and can perform poorly if n less than 30. It may also perform poorly if the data are not normally distributed. The Rice rule is presented as a simple alternative to Sturgis's rule. Doan's formula is a modification of Sturgis' formula which attempts to improve its performance with non-normal data. Where is the estimated third moment skewness of the distribution and where is the sample standard deviation? Scott's normal reference rule is optimal for random samples of normally distributed data, in the sense that it minimizes the integrated mean squared error of the density estimate. The Friedman-Diaconis rule is, which is based on the interquartile range, denoted by IQR. It replaces 3.5s of Scott's rule with 2 IQR, which is less sensitive than the standard deviation to outliers in data. Where and are mean and biased variants of a histogram with bin width, and a good reason why the number of bins should be proportional to is the following. Suppose that the data are obtained as independent realizations of a bounded probability distribution with smooth density. Then the histogram remains equally rugged as tends to infinity. If as the width of the distribution, e.g., the standard deviation or the interquartile range, then the number of units in a bin, the frequency, is of order and the relative standard error is of order. Comparing to the next bin, the relative change of the frequency is of order provided that the derivative of the density is non-zero. These two are of the same order if is of order, so that is of order. This simple cubic root choice can also be applied to bins with non-constant width.